Welcome back all of you. So today is the last part of the introduction. Earlier we studied some basic definitions and the classification of energy sources, the definition of renewable energy and the need for renewable energy, followed by Indian energy scenario and global energy scenario, like what is the primary energy consumption, what is the electricity consumption. So in those scenarios, you might have seen the diagrams which were drawn in some specific format. So those balancing diagrams or the pictorial representation of the flow of any quantity, whether it's mass, energy, money, it's called a Sankey diagram. So in today's lecture, we will study about what is a Sankey diagram, how to draw it, and how it can be used in the energy sector. Followed by two very important concepts in the power sector. One is capacity factor and other is the load factor. Both are associated with the power plants which run on different fuels, and load factor is mainly on the utilization basis. And what's the difference and how both of them help like either electricity producers or the consumers to manage their supply and demand respectively, that we will see in this lecture. So Sankey diagram, it is a specific type of flow diagram and mainly used for visualization of material, cost or energy flows on a system level or regional level. Okay, we can draw a Sankey diagram for a small reactor, for a small unit or an entire power plant, or we can draw it for regions like for a town, city, state or a country, or even we can represent the global energy supply and demand using a Sankey diagram. It helps to identify the important contributions to a flow, mainly based on the size of the arrow or the width of the arrow. It can tell us which of the flows or whose contribution is higher and whose contribution is lower, and it shows conserved quantities within defined system boundaries. Conserved quantities means, suppose if input energy is, let's say, 100 megajoule to a system, output has to match 100 megajoule. It can include losses as well as useful part of the energy, but since input was total 100, total output including losses has to match 100, then only the Sankey diagram would be balanced and can be drawn correctly. So that's one basic requirement. It is applicable to the quantities which can be conserved. It has directed arrows. The directions of the arrow shows the supply to demand, or like from where to where the energy is transferring or mass is transferred or money is flowing. Okay, and it has directed arrows between at least two nodes. It can have multiple nodes, like higher than two nodes also. Suppose energy is transferred from A to B, so we can represent it by one arrow. But if energy is transferred from A to B, C, D, multiple, so we can have multiple arrows. Okay, so it has directed arrows and it should have at least two nodes, and it can have higher nodes also, which features different flows in a process, production system or a supply chain. And the most important thing after these 2 points, one is quantity should be conserved. Second, at least two nodes should be there so that it has directed arrow to show the direction of the flow. And third is the width of the arrow should be proportional to the flow quantity. For example, if we represent this width by the value, so 10 megajoule, so obviously the 5 megajoule should be something half of this. Okay, it cannot be like very small or it cannot be bigger than 10 megajoule. So that proportionality should be maintained, and the width of the arrow, it is proportional to the quantity of the flow. And this Sankey diagram, though in definition or in the first line I have mentioned, it can be used for material, cost or energy. It can be used for multiple quantities in varied range of applications like energy, material, supply chain, business, marketing analysis. It's a widely used tool. Let's look at some examples so it is more clear to you. We'll start with some simplistic examples and then we'll look at some detailed one, how it can be helpful to visualize complicated or a comprehensive system in a simplistic manner. This is a Sankey diagram for a typical electric hand dryer. So you know how electric hand dryer works. You plug the socket into the switch port and switch on the button, and the electrical energy is converted to kinetic energy because there is a blower, a fan which blows the air, hot air. It makes a lot of sound also, hand dryers, so sound energy, and then it provides hot air. So there is a generation of heat, thermal energy. So most of this heat is going to thermal energy. So you can see if this width is represented by 750, this is representing 550, it's proportional, and these two widths are 150 and 125. Just now, like that based on the definition what I told, I think this diagram is giving a wrong representation, because 150 joule line cannot be thinner than 125 joule, right? Either this should be 150 and this can be 125 to make it correct, or else the values should have been changed, or the width of the arrows should be changed. Okay. So this example which we have shown, even though some representation, the conversion and flow is correct, the Sankey diagram is wrong. This is a mistake there. The second example is of energy balance for a coal power plant. So you know what happens in coal power plant, you burn coal and then generate steam in boiler which goes and runs turbines, and then it is connected to the generator which generates electricity. So if you just do a basic simple Sankey diagram depending on the coal's potential energy which is supplied to the power plant. So almost 35 to 40% is the efficiency of power plant. So 35% is converted to electricity, almost 45% is lost, and 10% are lost or either used in power generation or is lost in generator. So you can see this Sankey diagram is much more appropriate and correct. We don't know the values, but if we know the percentage wise, that representation is also correct. In fact, more than the values, percentage wise representation is easy for decision makers to understand, because once there are values, we will have to do some addition and subtraction and then convert it to percentage to find it out. But Sankey diagram, the picture itself gives you the clear indication like which of the flows are important, which of the flows are not important, which of the flows represent useful energy, which of the flows represent losses. Just by looking at the width of the arrow, we can tell that. This is a Sankey diagram for a solar PV power plant, a detailed one where all the major power plant inputs or components are concerned. So that's the solar energy incidence. Let's assume that 10,000 megawatt hour is the energy incident on that solar PV array field. So out of 10,000 megawatt hour, almost 20% is converted to power, the DC power, and 80% is lost either as thermal losses 78% and optical losses like say 2%. Then this DC power generated, it goes to the power conversion system where we convert it to AC, and inverters usually have high efficiency. So out of 2000 you can see almost 1800 is converted to the AC power, with 50 and 150 megawatt hour getting lost, either it's DC losses or as inverter losses. And then when it is sent to the substation or step up transformer, and what we can use actually, it is little less than 1800, it is 17660, because in stepping up or substations there are not huge losses. So small amount of electricity or energy is lost in those stages. So you can see this is also one way of representing the Sankey diagram or the energy flows, where in the middle of the arrows we are representing a system, like what is the stage at which that transformation is happening. So here it's a solar PV array field, there is a input energy going, output energy going, then we have power conversion system where we have input and output, then we have substation and transformer where again we have input and output. So this way also we can represent the flow using a Sankey diagram. One last one, or maybe I think couple of them, for fixed bed down drop gasifier. So it's like for biomass, if we have a like big gasifier you add biomass feed into it, and it's a downdraft gasifier. So the producer gas will come from the bottom, and then the ash will be collected at the bottom only, because there is a grate above which the feedstocks will rest. From here you can send air or any gasification agent. So, and typically in downdraft gasifiers, along with biomass, to prepare the initial bed, we may use some coal also, like 1 or 2 kg coal for 40 kg batch reactor, and that way. So the energy which is going into the gasifier, it is coming mainly from biomass and coal, and the energy which is coming out of the gasifier, it is coming mainly in the form of producer gas and the sensible heat of producer gas. So this is the gasifier, the batch downdraft gasifier, and you can see it's like almost 2 meters tall height for this 40 kg batch. Pellets are fed into the gasifier, the biomass pellets and the coal. So the energy wise, you can see, since coal is a very small amount, like say 2 kg or 1 kg or 3 kg or 2.5 kg, and pellets would be like 38 kg or 37 kg. So based on the calorific value, we have the energy going in, and whatever is converted to producer gas, the cold producer gas, it is around 51%. And since the gas which is coming out of the gasifier, it will be very hot, it will have some sensible heat also. So that accounts for almost 17%. So the energy efficiency of gasifier, if you talk about thermal energy efficiency, so it's like 51 plus 17, so almost 68-69%. And if we are talking about cold gas efficiency, it is 51%. So Sankey diagram also helps you to calculate the efficiency of the process. And then there are some losses of energy which goes with the residue or as a heat loss. This is the last example for supply and demand of hydrogen globally, and the unit is million metric tons. So at present, if we take into account the global hydrogen supply and demand with respect to 50 million metric ton, we know that most of the hydrogen is a grey hydrogen. Grey hydrogen is the one which is produced from fossil fuels, mainly by steam reforming of natural gas and coal or naphtha. Okay, so you can see 20 out of 50, almost 23, 15 and 10. So very close, like almost 45%, more than 90% of the hydrogen is coming from fossil sources, and very small amount, like less than 5% or close to 5% is coming from electrolysis and renewable grid. Now that accounts total for 50 million metric tons. Where is it being actually used? So most of the hydrogen is used in the refineries and in fertilizer sector or ammonification, like we convert it into ammonia, ammonium nitrate. And in refineries, there are two processes which consume lot of hydrogen, it is hydrocracking and hydrotreating. So 17 plus 47, again 45% is consumed in the two sectors only, and very small amount of fractions of hydrogen are used in fuel cells, metal, glass industries, food, beverages, pharmaceuticals and plastics. And accordingly, you can see the width of the arrows in the Sankey diagram are changing. So one way to understand global hydrogen supply and demand would be going through lot of data which is in the form of a table taken from variety of sources of literature, and that way is this Sankey diagram, which is in a very simplistic way gives us a overall like overview of entire hydrogen supply and demand throughout the globe. So that way Sankey diagram is very helpful to make representations of either energy or the supply and demand related to energy and energy quantities. The next topic that we are supposed to cover is capacity factor. So it is related to the power plants. So as the name indicates, like every power plant has some installed capacity. Like let's say we set up a 1 megawatt power plant. If it is the rated capacity, when we actually use that power plant, we won't be able to get 1 megawatt, because there are certain many reasons because of which we cannot operate the plant to its fullest capacity. There would be certain losses, there maybe there is sometimes there is shutdown, okay, and efficiencies are limited. So if the plant is rated at 1 megawatt capacity, and we are unable to run it at full of its capacity because of certain reasons. So, whatever capacity we are running, that will help us calculate the capacity factor of that power plant. So, there are two terminologies which defines the capacity factor. One is installed capacity and second is the actual electricity generation. So, what is installed capacity? If you remember the first lecture slide, in India how much we have installed capacity? Almost 524 gigawatt. That is our installed capacity, and even if we run it for say 24 hours a day, it won't be giving us 524 into 24, because each of the power plants based on different sources will have different capacity factors. So, installed capacity is maximum rated output of a power plant, and that maximum output can be produced under ideal conditions which hardly exist. Unit will be in watt, kilowatt, megawatt or gigawatt. And actual electricity generation is what we are actually getting, like what is being produced through that power plant over a specific period of time. So, you multiply that power by time and you get kilowatt hour, megawatt hour or gigawatt hour. That is the actual electricity generated. Now, capacity factor is the ratio of actual generation by installed capacity. Okay. So, it is always going to be less than 1, because we cannot generate more than what it is designed for. So, ratio of actual output over a period of time to its potential output if the plant operates at full installed capacity indefinitely or continuously. So, in the form of formula you can write it as megawatt hours of actual electricity generated upon rated capacity, or sometimes it is also called as nameplate capacity, and into time. So, if once we have these three quantities, we can easily calculate the capacity factor for any of the power plants. So, by different energy sources, these are some of the numbers in 2024, and you can see nuclear, geothermal and gas based, they have much higher capacity factors than coal, hydro, wind and solar and the simple cycle of natural gas. So, you can see the renewables have lower capacity factor. And why is that? Because sun, wind, they are not available all the time, they are intermittently available, and so power plant won't be able to operate for 24 hours day and night in all the seasons. Whereas, like the power plants which run on nuclear, geothermal or even coal, if we have sufficient fuel in our storage, it can be operated continuously. It is possible to achieve higher capacity factor in these power plants. Like nuclear, very small quantity of fuel is able to produce a lot of power, and that much is already kept in the stock. So, we do not need to rely on daily supply. Whereas, in coal power plant, even though it is possible to do like store, but because of lower energy density, much lower energy density than nuclear fuel, we need huge amount of coal on a daily basis. So, storage is not possible for a long period, and that is why it does not go to as high capacity as nuclear. But in geothermal, again it is dependent on the earth's interior heat, which is not affected mainly by the seasons or day and night. So, it can be operated continuously. The reasons for these plants going at lower capacity, other than the source of energy, there may be some additional reasons related to maintenance and operations, or reliance on utilities or ancillary consumption of electricity. So, all those factors would govern the capacity factors. The reasons for reduced capacity factor, some of them are listed here. Plant is out of service, maybe there may be some operation and maintenance issues, or laborers are on leave or on strike. If they are absent, then the plant can be out of service and it will be operating at reduced capacity factor. Intermittency and unavailability. For renewable sources, this is a big problem. It won't be available for all the time 24/7, and for other fossil fuels, there may be like less availability or varied availability. Like biomass, it may not be available throughout the year in required quantity. So, that is another reason. Grid curtailment. Sometimes because of the reduced demand, the grid may be oversupplied and electricity is not actually needed. So when that scenario is clear, the power plants would prefer to operate at lower capacity, because whatever electricity they are producing, it may not be required and grid is already oversupplied. Economic dispatch. If for certain power plants, the production cost of electricity is higher than the market price of electricity, so during such time, they won't prefer to run it and produce electricity because it's not going to be profitable. So that's economic reason. Then many power plants, they sometimes go for ramping and starting up times vary, which changes their efficiency. So those are the other reasons. And now with global warming and climate change taking the central picture on the globe, environmental regulations. Also sometimes ministries can instruct, or pollution control boards can instruct power plants to operate at lower capacity during certain times of the year. Because like in North India, during the months of winter, during the time of harvesting of rice crop, the pollution increases a lot, air pollution. So that time the power plants in the nearby area may be asked to operate at lower capacity, so that net emissions coming from at least power plant are reduced and the conditions are well taken care of. So these are different reasons for reduced capacity factor. There may be a few more. Let's take one example on capacity factor, like how do we calculate it and how it is useful. So plant A, let's say nuclear plant, has a rated capacity of 50 megawatt and it produces 40,000 megawatt hour in 1000 hours. Plant B, it's a solar based plant, has a rated capacity of 100 megawatt and produces 20,000 megawatt hour in 1000 hours. Which plant has a higher capacity factor? If you remember that figure which I showed, like the comparative capacity factors of different power plants, answer is obvious, nuclear is going to have higher capacity factor. Let's check for this numerical. So what would be the capacity factor for nuclear power plant? Actual electricity generated, how much it is? 40,000. And what is the nameplate capacity or rated capacity? It's 50 megawatt into operating for 1000 hours. So it comes out to be around 0.8, that is 80%. So capacity factor is 0.8 for nuclear. Capacity factor for solar, similarly, it is producing 20,000 megawatt hour. Rated capacity is 100, operates for 1000 hours. So 2 by 10, 0.2. So obviously the capacity factor for nuclear is much higher than solar. So nuclear based plant, that is plant A, has a higher capacity factor than plant B. Now what is the significance of capacity factor? Like once we know what is the capacity factor, or based on the value of the capacity factor, how does it help the different stakeholders involved in the power sector? The first significance is it actually helps to determine what is the actual energy generation over time. If we know the periodic capacity factor for a power plant, we have some idea that okay, in 1 year this much energy can be generated. It drives the cost of electricity, because if capacity factor is higher, per unit cost would be lower. Once the plant is installed, already we have put the capital cost. For operational cost, it won't vary much with the changing capacity except for the cost of the fuel, but other cost may be like constant. So if we have the higher capacity factor, per unit electricity cost is going to be lower. So it drives the project financial viability also. It directly affects the revenue, internal rate of return and payback period for the power plant operator or owner. It indicates resource availability and site quality. If we have like historic data of capacity factors or for a plant, we can like based on the capacity factors, some indications can be made based on whether the resource or the fuel is available and what is the quality of the site to produce power. It supports grid reliability and planning, and it prevents overestimation of installed capacity. Suppose we have a solar based power plant in one part of the world and we know its installed capacity and capacity factor. So, while planning a similar power plant in some other part of the world, having knowledge of the capacity factor of those power plants will help overestimation of installed capacity in other parts of the world. So, that way it is a significant value. So, that was all about capacity factor. The last point for today, that is load factor. So, just like capacity factor is from the production side, like the supply side, the power plant side, load factor is from the utilization side. It is defined as the ratio of average load over a given period of time to the maximum demand or the peak load occurring in that period. So, this load or demand is from customer side, okay, it's from the grid user side. In terms of definition, it's average load by peak load. Average load is total energy generated, peak load is the maximum demand into time. So, it actually determines how efficiently we are using the energy which is produced. Capacity factor tells us how much of the energy is actually produced compared to its rated capacity, and once that energy is produced, how efficiently we are able to use it, that is determined by the load factor. So, basically it is a load factor which can influence or govern or give some idea to capacity factor and not vice versa. Okay. Demand can like help change or manage the supply, but supply won't manage the or like govern the demand. So, demand patterns can determine how much of the installed capacity is to be actually utilized. So, if the load factor is high, it will ask or it will force power plants to operate at higher capacity factor. But even if power plants can operate at higher capacity factor, but if the load factor is low, it will give some relaxation to the power plants and ask them to operate at lower capacity. Let's take one numerical example where we have these combined concepts of load factor and capacity factor. A coal fired power station, it has rated capacity 1000 megawatt. It is designed to supply power to a nearby city whose peak demand in summer reaches maximum of 800 megawatt. So, we have peak demand is 800 megawatt, rated capacity is 1000. Annual average power consumption is 600. The coal plant always generates exactly what the city demands. Calculate load factor of city's usage and capacity factor of the power plant for that year. So, let us calculate load factor first. It is the average load by peak load. So, average load is 600 megawatt for that city. Peak load is 800, which reaches certain times during summer mainly. So, 600 by 800, it comes out to be 75%. So, load factor is 75%. It means the city's demand is almost 75% steady, and the grid or the utility, they have to keep some extra equipment ready to manage that 800 megawatt peak demand, or else most of the year the city needs only 600 megawatt. But even if for one day, if it is reaching 800 megawatt, the equipment has to be ready. So, utility has to keep that much extra equipment ready. So, that is what governs the load factor. It is based on the demand of the city and how they are using the power. Now, what is the capacity factor? Actual generation by the installed capacity. So, installed capacity is 1000, actual generation, average is 600, but sometimes it needs 800 also. So, if we look at actual energy produced based on the annual average is 600 megawatt, it is for 1 year. So, 1 year it is 365 days into 24 hours, it comes out to be 8760 hours. So, if you multiply by that, we get 5 some megawatt hour, and the maximum potential energy or the installed capacity, it is a 1000 megawatt. It is when we multiply it for 1 year, 8760, it comes out to be 8764 times 0. So, capacity factor would be the ratio of these two, actual energy produced upon rated capacity into time, which is around 60%. So, capacity factor of the plant is 60%, load factor is 75%. What is the significance of these two values? See, 75% of load factor means it is a high value actually. It tells us the city has a fairly consistent demand for power throughout the year. Okay, and capacity factor of 60% tells us, even though it's slightly lower value compared to load factor, we say that plant is oversized because the demand is 600 megawatt. We have designed the plant for 1000 megawatt. But even though, let's forget about the average demand of 600 megawatt, even if we take the highest 1 day or 2 day demand of 800 megawatt, that is the highest need, our plant is still over designed. So, if the highest demand is 800 megawatt, I think even 810 or 820 megawatt plant would have solved the city's situation. So, that way load factor or capacity factor can help us guide whether the supply is proper, whether the demand is proper, and based on the demand, how to manage or govern the supply. Let's look at like comparative distinction or differences between the two factors based on different features. So, capacity factor and load factor. The perspective is capacity factor is based on the supply side. It measures utilization and performance of the power plant, okay, based on its capacity and based on actual electricity generation. Load factor, it's on the demand side. It measures the consistency and efficiency of consumption or use of energy. Once it is produced, how efficiently, how consistently it is being used, that tells us that is told by load factor. Primary variable here in capacity factor is rated capacity. It is a fixed quantity. It's a hardware limit. It's a physical hardware limit of that power plant. It cannot go beyond that particular number. But load factor, it depends on the peak load or the demand, which is human centric. So, it's a variable and behavioral metric. It's not fixed or constant. Capacity factor indicates the reliability of plant, the availability of resource, and operational efficiency of the power plant. Whereas load factor, it tells us how stable the grid is, how efficiently the electricity infrastructure is being used, how efficient are the transmissions, and how efficient are the usage appliances which consumes the electricity. The preferred value for both the factors is obviously the higher the value, better would be the cost. So, if we have a high capacity factor, it can help us lower the unit electricity cost and for quick recovery of capital cost, because whatever is money is being invested in setting up that infrastructure, it is a capital cost, and to be able to recover that capital cost soon, maximum utilization of that setup is preferred. High load factor is also desirable because it will tell whether the demand is steady or not, and once it is known that demand of electricity or any like power in a region is consistent and steady, accordingly the new power plants can be designed. Primary stakeholders who would be interested in capacity factor values would be the owners of the plants, operators, and investors who put money in the power plant, like mainly on the generation side, supply side. For load factor, it will be mainly the utility companies, the grid operators, and consumers who are involved in, once that electricity is produced, how to transmit or distribute it and how to consume or use it. So, that this sort of summarizes the difference between these two factors. One is capacity factor, other is load factor. So, I think that was all for today's lecture. Just to summarize, we started with Sankey diagram, which is used to represent or the visualization of different quantities. It can be mass, energy, cost. You can represent all the values which can be easily conserved. It should have direction between at least 2 nodes or multiple nodes, and the width of the arrow should be proportional to the numerical value or the magnitude. Capacity factor, it tells us actual electricity generated by installed capacity, and it is governed by the supply side. Load factor, it is the average load by peak load, and it is governed by the demand side. And then we saw couple of numericals related to capacity factor and load factor. to help you understand these concepts. So with that, we'll stop here. Thank you.